Hi, welcome back to Blockchain Fundamentals with Bill Laboon. Today we're going to discuss sidechains and cross-chain communications. So let's first think, before we get into the details of what we're going to do, what the problem is. What are we trying to do? Let's say you have some coin X and you would like to trade it for some coin Y in a trustless way. Now, if everything is on the same blockchain, this is a much easier problem. So we actually can see there are a lot of decentralized exchanges on blockchains such as Ethereum. So you think of Uniswap, converting one token for another is perfectly easy as long as all of these blocks are on the same chain. Which is why Uniswap works with ERC20 tokens, but can't access Tron or Bitcoin or directly, or Zcash or some other tokens running on another chain. There are a lot of problems anytime you're trying to interact with another chain, or really anything off the particular chain you're operating with. So if you'll recall when we discussed oracles and the oracle problem, you can think of interacting with another chain as simply another sort of subset of oracle problems, where I don't understand the rules for some other chain, and so it's hard for me to interact with them. Now, that doesn't mean that there are no problems interacting and converting tokens on the same chain, such as there's front running, there's liquidity issues, just letting people know that the exchange exists. But the actual transfers and understanding how they can be done trustlessly is pretty straightforward. So how do you do it? Well, the easiest answer, if you're not so worried about trustlessness, is using a centralized exchange. But there are some decentralized ways to do this, and that's really what I want to discuss. So how can we ensure that we can trade and interact and communicate across chains using only the chains themselves, not using a third-party service, not using a centralized exchange, etc. That's where I think it gets really interesting. So it turns out that there are some ways to do this. And I'll start with a relatively simple one of atomic cross-chain swaps. So you may have heard of atomic swaps. They are a way to atomically, that is unsplittably, perform a transaction that will swap coins across a network, so that at any point a user can actually decide that they are going to stop this transaction, or I shouldn't say at any point, up to a certain point, that the transaction will be stopped and the whole thing will be rolled back. So an atomic transaction is a transaction that either the whole thing happens, that is, person A gives their token X and gets back token Y, and person B gives their token Y and gets back token X, and either the whole thing will happen or not. There's no way that person A's transactions will go through and they'll get token, they'll send token X, but they won't get Y, and vice versa. So it is a little complex and a bit slow, but it certainly works. So let's go and start with an example. So our old friends Alice and Bob want to swap Litecoin for Bitcoin. So Alice has some Litecoin and Bob has some Bitcoin, and they would like to trade with each other. So Alice is going to do a few things. First, she's going to generate a refundable deposit of a certain amount of Litecoin, and then she's going to be able to claim B Bitcoin in a certain time. So before a particular time limit, T sub 2. And then Bob is going to claim his Litecoin at some point after that. So both Alice and Bob, to do an atomic swap, are going to have to generate a few different transactions. So here's how Alice is going to generate her refundable deposit of Litecoin. she generates some random string x and computes its hash. Okay, and remember, a hash is a one-way function. She then generates a transaction we'll call deposit A, and in order to for this transaction to work, they're either going to have to know the hash of string x and have this message signed by Bob, or signed by both of them, that they both agreed that it works. So think of it as almost like a 2 of 2 multisig. But she does not publish this deposit A transaction. She then generates a time-locked refund transaction, and so it's time-locked. She can't, so it can't happen until after some time t sub 2, and gets Bob to pre-sign this. So Bob already has his signature on it, so that it can be sent. And Alice now publishes her deposit A. So she hadn't sent it before she told Bob, had Bob sign refund A, but holds back the refund transaction. So she has the refund transaction as sort of a way to get a refund if Bob does not follow through on his side of the bargain. Meanwhile, Bob does basically the counterpart to this. He generates a deposit, which to unlock requires either knowing the value of X, which and signed by Alice, or a message signed by Alice and Bob. But again, he doesn't yet publish it. So Bob now generates the counterpart to his refund and gets Alice to sign that. So this cannot be claimed until after some time t sub 1. And remember, t sub 1 happens before t sub 2. So Bob now publishes his deposit B, holds back his refund B. So so we now, they've interacted, and here's where it comes time where they can decide what to do. So Alice can either decide to complete the swap, or she can change her mind. So Alice claims the Bitcoin by time t1. Remember, there are time limits to all this. And by claiming this, she's going to reveal X. Okay? If she issues that transaction, X is revealed because it's put on the blockchain. And now that X has been revealed, since Bob has a transaction that requires knowing X, he can claim Litecoin by any time t sub 2. So just a note here, when I talk about times, all of these times are block times. So remember, in a proof of work system that where block production times are probabilistic, then we can't really say this is going to happen by a particular timestamp. All of these are specified in blocks. All right, so the other thing that could happen, Alice changes her mind. So Bob claims his refund, which has already been pre-signed by Alice. So he gets his minus transaction fees. He is able to get his refund back, and Alice claims her refund. And everyone, again, minus transaction fees, is back where they started. So let's go through this. I think it makes sense to actually look at through time. So we have our two characters, Alice and Bob. Alice on the top, Bob at the bottom. Alice generates the value X, remember, which is a hash of a random string. She generates deposit A and refund A. She lets Bob know about this, so Bob generates the deposit B and refund B. After this, Alice publishes hash equals h of x and deposit. So once Bob sees that Alice has done that, he publishes deposit B. Alice can now claim the Bitcoin from deposit B, and in so doing, she's going to reveal X, the original value, right? Which again, it's going to be very easy to check because she's already published H, which is the hash of X, so we just rerun hash of X, so we know that that's correct. Bob now knows what X is, so he can now claim Litecoin because he already has the transaction signed by Alice. So this is in the good timeline. And so we can see a couple of things here. One, it's a bit of a complicated process. Now we can obviously script this, but there's still a lot of interaction happening here and things happening from one side to another in order to do it atomically and trustlessly. The second is the timing issue. So these claims have to happen. These claims have to happen. Alice's before T1, and then Bob's after Alice claims but before T2. And all of this is using probabilistic block production times. So at any point here, either the whole thing can go through, assuming that the Alice and Bob and or their scripts are paying attention, or the whole thing can be rolled back. So if we look back at our times, before A, there's absolutely no danger because nothing has even been sent out to the blockchain. No one has published anything. So obviously there's no danger here. Between A and B, Alice can always use her refund transaction to get get her tokens back. And between B and C, if we assume that Alice did the work, but Bob sees something wrong or changes his mind, Bob can get a refund up until point T1, and then Alice can get a refund after T2. And if it's any time after C, well, the transaction has been completed. So Alice has to send her coins on to make sure Bob doesn't claim the refund. Bob, same way. Like, as long as you're following the rules of this, it generally will happen atomically. Or it actually will happen atomically, rather. So if we look at, let's say we've got the bad Alice timeline here. So here, Alice is going to be bad. She's going to decide not to publish deposit A, which includes the hash of X. So here, if she doesn't publish it, so I've crossed it out in red, well, Bob just doesn't publish his deposit B transaction. If Bob doesn't publish that, Alice can't claim Bitcoin from deposit B. Bob can't claim Litecoin since X was never revealed, and so he just issues his refund B transaction, and Alice gets and refunds her own Litecoin transaction from refund A. So they just sort of revert back to where they were. Similarly, if Bob decides to renege, then he doesn't publish deposit B, so Alice can't claim Bitcoin, but Bob cannot claim the Litecoin from Alice since X was never revealed, right? So the hash of X was revealed, but not X. So instead, he just refunds back his Bitcoin, and Alice gets to refund her own Litecoin. So as part of this process, you will have to make sure that you move your tokens from this address, otherwise it could be refunded. So you can see that there's a bit of a going back and forth here with atomic swaps, but it does work out. So there are a lot of benefits to this. One, we don't have a middleman. There is no counterparty risk. At any point it can be rolled back. And it's entirely decentralized from a trading perspective. There's no central entity here. But one, it is much slower than a centralized exchange. Much slower, as you can see. How many transactions are being produced and have to go back and forth, and there's particular timelines. And when you have chains that have very different block production times, then you can, this could be extremely slow. You need to find a trading partner, and this might lead to centralization at this point. You can imagine, a centralized trading partner finder that, even though the actual trades themselves are decentralized, there may be centralization at another point. It's time bounded, so if you don't claim your coins, you can lose them. You could have a denial of service attack, right? So if you want to make sure that your claim doesn't go through, maybe you can try to DOS Alice or Bob. Theoretically, there is a very slim chance, astronomically small, if you don't set this up correctly in terms of timing, then the block production times line up in such a way that T1 comes after T2 or something like that. Now this would be, again, astronomically unlikely. You can imagine Litecoin blocks which happen every 2.5 minutes. Let's say that there's some just due to the vagaries of hash power going offline or something. Suddenly, Litecoin blocks are being produced every 30 minutes, and we have a few very fast Bitcoin blocks being produced every minute. you can imagine some strange issues occurring like that. So there are some problems with atomic swaps, but they were an early way of showing that cross-chain trustless communication is possible. So another way of interacting from one chain to another is sidechains. So sidechains have been, and the concept has certainly been around for a while, and there are a few out there that we'll discuss a little bit later in the lecture. But we can think of them as sort of altcoins on Bitcoin. They provide additional functionality while providing a peg to their initial chain. So usually Bitcoin. I mean, theoretically, you could do side chains on other chains. So you can do things like have Bitcoin escrowed, but generate tokens from this that operate on a separate chain and have those tokens interact back with the Bitcoin chain. Now, to do this in a full way, you really need more than what Bitcoin provides. But we can have essentially all the features of this by a simple hack called the SPV Trick. So using SPV, we don't have to interact with the entire chain. We can just look that the transactions we care about are in the longest branch that has received so many confirmations. And the script could just verify that a particular transaction occurred in the side chain using SPV. So it doesn't have to go in either direction. We don't have to look through and verify the entire chain. So using these SPV proofs, we can prove that something was included in the side chain. We can have sidechain block headers that show that a certain number of confirmations can go by. But generally, this is something that we have to be able to contest, because by using SPV, there always could be an argument, right, that we're not looking at the latest or the correct canonical chain. So this isn't foolproof, but it does ensure that any sidechain won't be able to hurt Bitcoin itself by doing this. Rather, we could have a problem with Bitcoin causing a problem for the sidechain, but that's much less likely to occur. We're sort of piggybacking on that incredible security that Bitcoin provides. So how can we do this, especially if we have very fast side chains? One of the things that people complain about with Bitcoin is that it is relatively slow, right? Transfers, if blocks are only coming on an average, mean time of 10 minutes, and you have to wait 6 confirmations before something is considered, sort of semi-finalized, probabilistically finalized, then a lot of the reasons for these side chains is we want to do things a little bit more quickly. So if we have really fast side chains, so like when I say fast, I mean a short time between blocks. Well, even an SPV node might not be able to keep up with them. We can imagine chains like Polkadot's relay chain, which has 6-second block times, or Ethereum, which is around 15 to 20 seconds. So you can imagine that like a Bitcoin node with these might not be able to keep up. So what we can do is use skip lists. And skip lists are similar to skip lists in computer science. We can sample proof of work and estimate the total work generated, so how much the weight of the chain is, in a sublinear way. What I mean by sublinear, it grows more slowly than the number of blocks. So here we're only going to point to blocks where the hash is less than the target divided by some value. So what we mean is if, let's say, the target is a million on the sidechain blocks, then we're only going to point to blocks where if m is equal to 4, where the target is actually less than 250,000. Or excuse me, where the hash is less than 250,000. So this should generally be evenly distributed, since a hash for a block is uniformly distributed between 0 and the target. So if we think of the target like here, where m is 4, So we have B5, B1, B5, and B11 are the only ones that are actually interacted with. And B4, B3, B2 are all going to point to B1, B6 through 10 are also all going to point to B5. So we don't have to actually keep track of every single block by doing this sort of proof of work sampling. However, since we do have a it is still a blockchain, it always can be verified, since each of these blocks is going to have a hash, reference the hash of the previous block. So there are a few notable Bitcoin sidechains. One is Mastercoin, which was later rebranded as Omni. So you may have heard it as Omni. Omni is probably most famous for Tether. Although Tether is now used on Ethereum and other blockchains, not just Omni. And Liquid Network, which offers a bilateral peg to Bitcoin with an asset Liquid Bitcoin, which has much faster settlement times. So I want to talk briefly about Liquid Network. How it works, you create some L Bitcoin by sending Bitcoin to a specific custodial address. And this address is watched over by the Liquid Federation. And once you send coins onto this custodial address, then a number of L Bitcoin on the Liquid network are minted. And these can be transferred very quickly, these L Bitcoin. It's 1 minute block times on the Liquid Bitcoin network with 2 block transaction finality. And then any member there can burn the L Bitcoin and unlock the Bitcoin from that initial custodial address. So what this lets you do is get this L Bitcoin, which can be moved around, and then somebody else can take that and convert it back into Bitcoin. This concept, which started with Liquid, has showed up elsewhere too. So there's wrapped Bitcoin, which is a very similar concept, but usually these are on Ethereum. So it's the same basic concept where you send some Bitcoin to an address, and there is some a smart contract instead of a federation here, but it's, again, same basic concept, that's going to mint a certain number of ERC20 tokens that represent the Satoshis that you sent on the Bitcoin network. And now this wrapped and again, someone can go to that smart contract and unlock Bitcoin back on the Bitcoin network, but transfer things, this wrapped Bitcoin around at Ethereum speeds, and much faster confirmation time, block production time, as well as interact with the rest of the Ethereum ecosystem, because it follows the ERC20 standard. So these are just a few of the ways that blockchains can intercommunicate and tokens can be represented on other chains. There are more technologies being developed right now, and in order to increase the ability for these chains to communicate. And I think this is something that we're going to see much more of in the future as a sort of corollary with the growth of the internet. So in the early days of networking, you really had specific types of networks, and specific networks themselves were sort of walled off from each other. You may have a network for all the people at IBM, but you would have a very different network that all the people at General Electric were using. And we saw this in the early days of the consumer internet too, where people would go to AOL or CompuServe or Prodigy, but they could not easily interact with people from other networks. But with the growth of the internet, all of these different systems were able to interact, and so what you see is sort of a growth of ability of new things to be generated and created as people are able to move seamlessly from one place to another and have different systems interact with some sort of very foundational protocol. So I think this is something we're going to see more of as we go forward in time, and I, for one, am very interested in seeing what gets produced once we do.